order derivatives because there are going to be occasions where you're going to need to take a derivative of a derivative. So in our first example, we are given a function and we have to find the second derivative. And I know that because of this notation, y double prime. This means find the second derivative. As I look at the problem, I'm thinking that I might need to use the quotient rule, but really I could clean this up using what I call the mu principle, many over one. And if I do clean this up, I end up getting a rewrite of the original function which says y equals x plus 2 minus 1 over x. Cleaning this up just a little bit more, I could say that this is y equals x plus 2 minus x to the negative 1. Finding the derivative of this will be pretty easy. The derivative is going to be 1 plus 0 plus x to the negative 2. Cleaning that up, we're left with just 1 plus x to the negative 2. The 0 doesn't really contribute anything. Now, I'm going to take the derivative of the derivative. Well, the derivative of 1 becomes 0, and then the derivative of the second term is negative 2x to the negative 3. Not wanting to leave negative exponents in our final answer, we get negative 2 all over x cubed. So that wasn't too bad, but there's something to note, and that is in this step right here, it's tempting to want to get rid of this negative exponent. Generally, when you're expressing your final answer, you don't want to have a negative exponent, but we have to take another derivative before we express our final answer. So it's best to just sort of leave it like this rather than rewrite it with a negative exponent. Moving to example 2, we have a trig function and we have to find the second derivative as indicated by this notation. So I'm going to start by finding the first derivative. And the first derivative from our last lesson is just going to be secant x tan x. Now, in finding the derivative of the derivative, we're going to need to use the product rule. So what I'm going to do is set up a little chart, f, f prime, g, g prime. F refers to our first function, and g refers to our second function. So our first function, f, is secant x. Our second function, g, is tan x. And we're going to take the derivative of each of these. The derivative of secant x is secant x tangent x, and the derivative of tangent x is secant squared x. Now, according to the product rule, to figure out the derivative when there's a product involved, it involves the formula first times the derivative of the second. Again, that's the first times the derivative of the second plus the second times the derivative of the first. So that's the second times the derivative of the first. If we clean this up, we end up getting secant cubed x plus secant x tan squared x. Factoring out a secant x, we're left with secant squared x plus tan squared x. Now I know when I see a problem like this with this sort of result, I'm tempted to think that we might need a Pythagorean substitution or something like that. So I'm just going to think for a moment what that identity really is. And I believe it's 1 plus tan squared is equal to secant squared. And there's really no way I can get this to look like that. So while it was a good thought, we're not going to use it. So the reality is that this is our final answer right here. Okay. And for our last example, They give us the fourth derivative, and they want us to find the sixth derivative. While it's tempting to think you can just sort of leap from one derivative to the next, you have to go in order. So after the fourth derivative, we must find the fifth derivative. And the derivative of 2x to the 2x plus 1 is just 2. And the derivative of the fifth derivative would give us the sixth derivative, and that's just going to be 0. So this is pretty easy as well. So these higher order derivatives aren't too bad. Sometimes they can get a little messy algebraically, but you're really just taking derivatives of derivatives. I hope this lesson helped.